screen. Now, the practical situation. So this is the two slits. So the slit width of the slit A is like 0.02 millimeters, and D, the separation between the slits, which is about 0.25 millimeters. Separation, that is D. So I'm going to erase that. That is the separation between slits, and this is the width of the slit, which is about 0.02 millimeters. This is the double slit. From there, you have like 1 meter to the screen. So this length is much bigger compared to these lengths, slit width and the separation. So if you consider two light rays which are coming to this point on the screen from these two point sources now, S1 and S2, we consider these slits, they now work as point sources. Now if you consider two light rays which are coming to this point from these two slits, these rays are almost parallel to each other. In this diagram we won't see that because this diagram is not according to a scale, but actually in real life these are almost parallel, like this. These two light rays are parallel. So if I consider the distance traveled by S1 to reach that point, let's say it is L1, and distance traveled by light ray 2 emitted by this slit to reach that point, let's call it L2, then the path length difference is the extra distance traveled by this light ray to reach that point. How do I find that? If they are almost parallel to each other, if I draw a perpendicular line to this L1, this is the additional distance traveled by light ray 2, which is the additional distance, let's call it L, no not L, let's get a different letter because we already have, using L here, so I'm going to call it path length difference equals L2 minus L1, which is this distance. For right now, let's call it X. What is X? Okay, so I'm going to draw another diagram to get this path length difference in terms of D and theta. Theta is the angle, this small angle in theta. Okay, so let me do the diagram here. So I have let's call R1, and this is R2 ray 2, and this is the additional distance traveled by the ray 2, and that is called path length difference, which is X in our case. And this is the angle theta. And now if I draw a line from the center of these two slits to the screen, a perpendicular line, so let me use a different color. center of the two slits is a perpendicular line from there to the screen, and they're going to the screen, they're going to meet somewhere here in the screen that is far away. So let's take this angle. So I'm going to draw another line parallel to these two rays. Now this angle is also theta. This angle is also theta, theta and theta. And this is this separation is D, that is for the separation between the slits. This is theta. Now I can see D, this is a right angle triangle. D sine theta, which is x equal D sine theta. And that is the path length difference, L2 minus L1. Now we know these two sources, when they emit this light, they are in phase. So if they travel the same distance, they should be in phase when they come to the screen. But because of this path length difference, there should be a phase difference. Now let's consider this x equals to lambda. Lambda is full wavelength. Then what is the phase difference between these two waves? No phase difference. Ray 1 and ray 2 is advanced by one wavelength. So when they come to the screen, they will be again in phase. So what you have? You will have a constructive interference. That means a wave with bigger amplitude. That will give a high intensity. So you will have a bright spot on the screen. Similarly, if you have 2 lambda, 3 lambda, or any integer number of lambda as the path length difference, then you will have a constructive interference. So what is the condition for the constructive interference? Constructive. For the constructive interference, path length difference, x equals d sine theta equals m lambda. M is an integer. M can have all these values: 0, 1, 2, 3, 4, up to all the integers. When m equals 0, there's no path length difference. Then you have the central maximum. When m equals 1, you have the first maxima. Now we are going in this direction. How about the negative numbers for the m? Also possible when you're going downward. So both positive and negative integers are possible as m. So I can write 0, plus and minus 1, plus and minus 2, plus and minus 3. That is the condition for the constructive interference. Okay, now let's consider destructive interference. Now assume this path length difference equals lambda by 2, half of the wavelength. X equals lambda by 2. Then what will happen? This is wave 1, this is wave 2, and this wave 1. Wave 1 is advanced by half wavelength. Then when they come to the screen, this is the phase relationship between these two waves. They are exactly in out of phase. So what you have? You have a 0 amplitude, no wave. zero intensity. So you have destructive interference. So what is the condition for the destructive interference? The destructive condition is path length difference x, which is d sine theta, equals m plus half lambda. M can have these values 0, 1, 2, 3, all the integers. So when m equals 0, path length difference is half lambda, you have destructive interference. When m equals 1, you have 3 by 2 lambda, again you have destructive interference. So that is a condition for the destructive interference. You can have destructive interference in both sides from the center of the screen. Center means where you get the central maximum. So if you go up or down from the central maxima, you will have minimas. So you can say when m equals 0, you have first minimum, and m equals to second minimum, like that.